What's going on, guys? Hope you're having a good little break here. But we got to do something, apparently. So I'm going to go through the practice problems with you guys, or for you guys, I guess I should say, not with you guys because you're not here. All I got is my little buddy. And he's tired. He's going to fall asleep pretty soon, so this is not for his benefit. But I just want to go through the practice problems and the conceptual problems. And then you guys can check your answers, copy down my answers, whatever works for you, to submit for me. And then we'll move on to the problem-solving problems in a little bit later on. All right, so first question here. Find the total charge of a system consisting of 3.9 times 10 to the 7th electrons. All right, so we have 3.9 times 10 to the 7th electrons. We want to figure out what the total charge is. Now, we know, if we read the PowerPoint or went through the PowerPoint, that one electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. All right, so if we have one electron has a charge of negative 1.6 times 10 to the negative 19th coulombs, and we want to figure out how much charge 3.9 times 10 to the 7th electrons is, we got to multiply those two, right? And you could set it up like the field goal post if you guys have ever remember doing stoichiometry stuff. Like if we have 3.9 times 10 to the 7th electrons, and we know that one electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. Electrons cancels, and we can just multiply across the top there. So we get 3.9 times 10 to the 7th times negative 1.6 times 10 to the negative 19th coulombs. And we can get an answer there. Now, for those of you that aren't sure how to do this, right, it's been a while since you've done multiplication with scientific notation. There's basically two ways to do it, right? If you got a calculator, which I do, you can do 3.9 times 10 to the, where's the caret? The caret's right there, times 10 to the 7th, right, times negative 1.6 times 10 to the negative 19th. You can press enter, and you get the answer there of negative 6.4. The E means times 10 to the negative 12th coulombs. All right, and we can get the answer that way. The other way to do it, right, if you don't have a calculator that can do scientific notation, is we can do it in parts. So we take 3.9, right, and we multiply that by the negative 1.6, and we multiply that. We take these two separate, right, 10 to the 7th times 10 to the negative 19th. 3.6 or 3.9 times negative 1.6 will give us negative 6.24. Did I write that wrong? Idiot. 6.24. Negative 6.24 times, and when we multiply numbers that have bases that are the same, what do we do with the exponents? We add them together. So 7 plus negative 19 is negative 12. So we could get it that way as well, right? Negative 2.4 times 10 to the negative 12th. Negative 6.24 times 10 to negative 12 coulombs worth of charge. All right, so there's number one. And I think I'm supposed to be available all day tomorrow, so if you guys have questions, you guys can shoot me an email or message on Schoology. and I'll be here to respond to them. So there's that. Number 2, how much negative electric charge is contained in 2 moles of carbon? Now, we're really going back to chemistry, and I gave you some hints on the PowerPoint to kind of help you out here. So we actually do end up doing what you guys used to do in stoichiometry. So 2 moles of carbon, right, is what we're going to start out with. And then we want to find conversion factors that'll eventually get us to electric charge. So moles, 1 mole of carbon, and I wrote this on the PowerPoint, is equal to 6.02 times 10 to the 23rd atoms. That's Avogadro's number for you, those of you that don't remember that one. And 1 atom of carbon contains 6 electrons. Now, how did I know how many electrons are in an atom of carbon? Well, carbon is the 6th element, right? Its atomic number is 6, which means it has 6 protons, and the electrons is always equal to the number of protons. So if we have 6 electrons, or 6 protons, we also have 6 electrons. So we get that. And then, just like we did in the last problem, 1 electron has a charge of 1.6 times 10 to the negative 19th coulombs. Negative 1.6 times 10 to the negative 19th coulombs. So there's all the conversions there, right? Moles will cancel with moles, atoms will cancel with atoms, electrons will cancel with electrons, and we end up with coulombs, which is charge. So all we got to do is multiply across the top. So 2 times, let's do a parentheses, 6.02 times 10 to the 23rd times 6 times negative 1.6 times 10 to the negative 19th. And same thing that we did last time, right? If we have a graphing calculator, a scientific calculator that can multiply scientific notation, we can just plug all that in. If we don't, we can do it pieces. I'm going to do it pieces so that those of you that don't have scientific calculators can kind of follow along. So we'll take the starting numbers, 2 times 6.02 times 6 times negative 1.6 times 10 to the 23rd times 10 to the negative 19th. So we do all this stuff first. 2 times 6.02 times 6 times negative 1.6 will give us negative 115.6, we'll call it, times 10 to the 23rd, 10 to the negative 19th. That'll give us 10 to the 23 minus 19 should be 4, 10 to the 4th power. So we get 115 times 10 to the 4th coulombs. Now, for those of you that just plug it into your calculator, you'll probably get something different because scientific notation, right, we shouldn't have 115. We should have, right, a single number and then the decimal point. So if we move this 2 more places to the left, right, 1, 2, that'll give us negative 1.156 times 10. And because we moved the decimal place 2 places to the left, that increases this by 2. So we get times 10 to the 6th coulombs. All right, negative 1.156 times times 10 to the 6th coulombs worth of charge in 2 moles of carbon. All right, so those are the practice problems. Now we're going to move on to the lesson check concept questions. All right, and these will be a little bit more explanation than just math, so let's talk through these. If an object is electrically neutral, what can you say about the amounts of positive and negative charge it contains? So, if we have something that's electrically neutral, that means the charges are balanced, right? Neutral means the positives and the negatives are canceling each other out. So what can we say? We can say it has the same number of positive and negative charges. Right, and that'll give us a neutral charge. If we have the same number of positives as we do negatives, those will cancel out, and we get neutral. What we can't say, right, this is a bad thing, we don't want to say this, is that it has zero charge. Right, we can never say something has zero charge. We can say it has positive charge and negative charge, and they cancel out to make it zero. But to just say that an object or a substance has zero charge or no charge, that's wrong, because everything's made up of atoms, right? And atoms are made up of protons and electrons, which means everything has charges in it, right? Sometimes those charges will cancel out and give us zero. So we can say has the same number of positive and negative charges that cancel out to give us zero. We can't just say that it has zero charge or no charge, right? That doesn't make sense. Everything has some charge. Whether the charges cancel out or don't cancel out is how we kind of determine whether it's neutral or positive or negative. All right. Number 4. What does charge quantization tell us about the amount of charge an object can have? So charge quantization means that charge comes in very specific numbers, right? The smallest charge we can have is the charge of an electron, which is 1.6 times 10 to the negative 19th coulombs, right? That's the smallest possible charge we can have. Electrons are a building block of matter, right? They're a fundamental particle. So we can't have anything smaller than 1.6 times 10 to the negative 19th, which means everything else has to be a multiple, or every other charge has to be a multiple of 1.6 times 10 to the negative 19th, right? And I think I gave you guys an example, right? Let's just do another one, right? If we, for example, say something has a charge of negative 3.2, 4. Like negative 4.8 times 10 to the negative 19th coulombs, right? Just to give an example. That's fine, because 4.8 times 10 to the negative 19th, right? 1.6 goes into 4.8 4 times. So this means the object has 4 extra electrons, right? And we can have 4 extra electrons, that's fine, because 4.8 is a multiple of 1.6, right, times 10 to the negative 19th. Now, what can't we have, right? We can't have something like negative 5.6 times 10 to the negative 19th coulombs, right? Why can't we have something like negative 5.6? Because that would be 4.5, right? 1.6 goes into 5.6 4.5 times, if I did my math right. Let's double check that. 5.6 divided by 1.6. 3.5. What an idiot. Oh, that means this one's 3 too. I'm stupid. 3.5 extra electrons. And what can't we have? We cannot have half an electron. There's no such thing as half an electron. Or any kind of decimal place, like a quarter of an electron, an eighth of an electron, it doesn't matter. You can't have it, right? It has to be in full numbers of electrons. So something like this, definitely possible because it's a multiple of that 1.6 times 10 to the negative 19th. Something like this, definitely not possible because we get that half, and we can't have half an electron. It's not a thing. All right. Number 5 is the total amount of charge in the universe changed when we charge an object. Quick and easy answer is no, right? We can't have, or the charging an object doesn't change the total amount of charge in the universe. It's just like when we did energy, right? Giving something energy doesn't change the total amount of energy that we have. It just moves energy from one place to another. So, no, the charge is moving or transferring from one place to another. All right, it doesn't disappear. It doesn't change the total amount of charge. It just moves from one place to another. All right, 6 is a long one, but pretty straightforward. We have an electrically neutral object given a positive charge. So we have something neutral, and we're going to make it have a positive charge. Does the object's mass increase, decrease, or stay the same? And then choose the best explanation. So I think it's easier if we kind of read the explanations first and then make a decision. So to give the object a positive charge means removing some of its electrons. This will reduce its mass. All right, so this is the explanation for reducing its mass, right? The mass decreases. Since electric charges have mass, giving the object a positive charge will increase its mass. So there's our argument for the mass increasing. Charge is conserved, and therefore the mass of the object will remain the same. There's our explanation for the mass staying the same. So if we read through these, to give an object a positive charge means removing some of its electrons. So when an object, well, let's just say the answer is A. The answer is A, and the mass is going to decrease. If we look at an atom, right, we have our nucleus. Let's say we have something that's got 4 things in the nucleus, and 1, 2. The first shell's only supposed to have 2. I messed up. Well, we'll make an inner shell. 1, 2. All right, so we've got, let's make it 1, 2, 3, 4 protons, a neutron, and 4 electrons. So when an object becomes charged, right, or when we look at moving things to make something become charged, right, the center of the nucleus is positive because that's where all the protons are. The outside of the atom is negative because that's where all the electrons are. So when we're moving things, right, or when we're trying to charge things, it's a lot easier to move the things that are out here, right, the electrons, than it is to move the things that are in here, the protons, right? We can't just, and actually if you think about it, right, if we take something and we change the number of protons, we're actually changing the element itself. So taking things from the inside, it just doesn't work. So the way that we charge things is not by moving protons, it's by moving electrons. So the electrons, let's say this one is like, gets bored, it goes away, right? This electron leaves, so we had 1, 2, 3, 4 electrons and 1, 2, 3, 4 protons. We were neutral. If this electron's up and leaves, now we only have 1, 2, 3 electrons and 1, 2, 3, 4 protons. Now this whole thing becomes positively charged, right? It was neutral, now it's positive, and it's positive because something left, right? And if something leaves, what happens to the mass? Well, the mass has to get smaller. So correct answer is A. To give an object a positive charge means removing electrons, which will reduce its mass, so the total mass decreases. And last, I believe, of the conceptual questions, if rabbit fur is rubbed with glass, what is the sign of the charge each object acquires? Now, to answer this one, we actually have to go back to the table that has the triboelectric charging. So let's take a look. Ooh. Take a look at this. Oops. Okay, so we are rubbing rabbit fur with glass. So if we take a look at this, right? Rabbit fur is all the way at the top, very positive, right? It likes to become positive. When we look over here, right? We can see how this works on the table. Things that are higher on the table will become positively charged when they experience friction with things that are lower on the table. So if we look over here, right, things that are higher on the table will become positively charged when they're rubbed with things that are lower on the table. So if we rub rabbit fur, which is at the very top of the table, with glass, which is right below it, because the rabbit fur is higher on the table, it will acquire the positive charge, while the glass acquires a negative charge. So the rabbit fur will become positive because it's higher on the table. Glass will become negative. So the table here really just is a representation of how willing things are to give up and take electrons. So things that are near the top of the table, right, which are like to become positive, they're very willing to give up electrons, right? Rabbit fur, glass, human hair, they want to become positive, right? They want to give up electrons, so they give up electrons very easily. Things that are at the bottom that like to become negative like to take electrons, right? They like to hold on to electrons. They like to get more electrons. So things like Teflon and PVC and rubber like to hold on to their electrons and actually get more electrons, right? So those become negatively charged. So if we were to take something like rabbit fur and Teflon, the bigger the difference between them on the table, the more charge they can acquire. So when we do this example, rabbit fur and glass, right, we don't get a huge charge because rabbit fur and glass are relatively close. They kind of want to give up electrons the same. Rabbit fur a little bit more, so it becomes positive. But if we were to do something like Teflon and rabbit fur, right, the rabbit fur will become really positively charged and the Teflon will become really negatively charged because there's such a discrepancy there in how much they want to give up and how much they want to accept electrons. All right, so that is the 19.1 practice problems and conceptual questions. Fast asleep, I told you you would be. You ready? Hey, you fall asleep on me? Oh, good boy. All right, I'll put another video up with the practice problems, or the actual problems. All right, so you guys can check that out too.